So I will talk about Poisson submanifolds of rigid Poisson manifolds. So the first part of my talk, I will explain what these rigid Poisson manifolds are. You should think about them as being the generalization of duals of semi-simple compact Lie algebras in some sense. And, well, they are very nice because you have normal forms around any of their leaves, and also because they are rigid in the sense that they have no deformations. And now, their Poisson submanifolds, if you have a Poisson submanifold of such a rigid Poisson manifold, you immediately can deduce that it has one property, which I'll call S compact. So these ones are S compact. I will explain later exactly what this means. And the theorem that I want to, and this property is basically, you can define it only in terms of the Poisson manifold itself. The theorem that I want to discuss is an embedding theorem for this S-compact Poisson manifolds into rigid Poisson manifolds. So somehow this property actually characterizes them as submanifolds of rigid Poisson manifolds. So I will actually start by stating this result. So first, well, start with a Poisson manifold M pi, which is S compact. So let this one be S compact. And there are two conclusions. So basically there are two different theorems. So the first part is that, well, there exists such an embedding into a rigid one. So there is a proper embedding of this S-compact Poisson manifold into a rigid Poisson manifold. Okay, so this is the first part, and the second part, well, this embedding is important mostly because of the second part. The second part describes deformations of such S-compact Poisson manifolds. So part B tells you the following. So if you consider a deformation of this Poisson structure, pi, so let pi tilde be a second Poisson structure on M, which is very close to pi. So if pi tilde is close to pi, the nice thing is that you can actually realize it as a Poisson submanifold of the rigid one, which is close to the original one. So then it follows that there is a Poisson embedding of M and pi tilde, and I'll denote this by I tilde, into the rigid one, which is also close to the original embedding. So so in general, deformations of Poisson structures are pretty difficult to understand, and they usually have a lot of deformations. Now, in this theorem tells you that you can reduce this problem, in this case, to just deforming the submanifold inside the larger one, right? And then you can actually use it to compute the Poisson moduli space of such an S-compact Poisson structure. I'm not going to be more precise about that, but, well, a little bit maybe. So you can actually prove that you can parameterize Poisson structures nearby by nearby embeddings, reducing the problem of finding Poisson structures by finding such nearby embeddings. And this is basically looking at sections of the normal bundle of M inside the M bar, which satisfy a linear equation. So you reduce a quadratic problem to a linear one, which is much more simpler to understand. Okay, so what I will do, I will start with a very, very simple example of this phenomenon, which I hope most of you will understand immediately. So this is the first example. So consider the case of a symplectic manifold. Symplectic. And we'll also assume that S is compact. Now, if we add also this condition that its first fundamental group be trivial, then you can realize the completion as follows. So then S bar, the completion will be embedded into S times Rn as an open neighborhood of S times 0. And with symplectic leaf simply given by S times T1 up to Tn, and symplectic structure omega S, the symplectic structure on S plus a linear combination Pi sigma I, where these sigma i's are closed forms on S, and they satisfy the condition that basically they form a basis for the second theorem cohomology of n is the dimension, is the second Betti number of your manifold. Okay, n. Right? So this form a basis of H2 of n. Okay, so you obtain this Poisson manifolds which just contains copies of S, and in every direction it changes the cohomology class. Well, the cohomology changes exactly, well, takes all the values. Of course, this will be non-degenerate. This forms in some small open neighborhood of S times 0, right? But now you can see already part B. If you take a Poisson structure close to omega S, just by the Moser trick, you know that, well, it will be, well, first of all, it will be against symplectic, and then it's only determined by its cohomology class. And as you vary here, the cohomology class is in all possible directions. It corresponds to a nearby embedding, right? S is embedding as the S times 0, and it will be just embedded nearby. I hope this is clear, this example. Okay. So this is just a Moser trick. Of course, the general picture will be a bit more complicated. And now the second example of yes, it's some neighborhood around S times 0.
And did you tell us what S compact means?
This is a capital S. So here I mean that capital S. No, that I didn't tell you yet. And I'll tell you a bit later. Okay. And the second example of a rigid Poisson structure is the Lie-Poisson structure, or the linear Poisson structure on a dual of a Lie algebra. So this is rigid for G be semi-simple and compact. And compact. Okay, so this one is rigid. And well, the way I think about rigid Poisson manifolds is as a generalization of this example. Now, let me just tell you a few things about these Poisson structures, and then basically the definition of a rigid Poisson manifold will be will be exactly these properties that I'll list right now. So, first of all, if you take any symplectic leaf, G star is a symplectic leaf. The symplectic leaf itself will be a quadrant orbit, and it has the following properties. So first of all, S itself is compact, and it is also simply connected. Okay, and these two properties, I'll put the one next to them. And then second, if you, well, at some point x in S, you can consider the isotropy Lie algebra at X, Gx, which is basically, well, it is the stabilizer algebra of X for the quadrant action. So this is automatically a subalgebra of G, and this one is compact. Right, so I'll call this the second property. So compact means, well, it has some integration which is compact, but equivalently you can decompose it as a semi-simple plus compact, and compact one plus an abelian one as a direct product. And the third property, which maybe people are not that aware of, is the following. So you can consider the space, let's call it capital sigma, of points where the rank of the Poisson structure is exactly the dimension of S. Right? So the rank of pi g equals the dimension of S. Right? And this one has the following property. So sigma is isomorphic around S. So it is a submanifold, and around S it looks simply like a product. S times the dual of the abelianization of the isotropy Lie algebra. So by the abelianization, I simply mean Gx modulo the commutator. So it's basically the center of this algebra because it's compact. So sigma around S looks like this, and with a symplectic foliation, exactly like, well, similar to this one. So in particular, the leaves are, let's call them S times T, comma, omega S plus some omega T, where this map, which sends T to the cohomology class of omega T, so from Gx AB star to H2 of S, this one is a linear isomorphism. So it's a linear.
What is it that you are describing here? So the sigma was the subset of S?
Yes, of G star. And I was saying that the subset is in fact a submanifold which around S.
Oh, it's a subset of G star.
Yes, it's the set of points where the rank is the same as the dimension of S. And what happens is, well, you can choose the right coordinates on this space such that this is a linear isomorphism. So basically this tells you what? That the sigma in here is precisely the completion or the rigid completion of S. Right? So through every leaf you have, so let's just write it like this. Sigma is isomorphic to the completion of S around S. Right? And that happens at every leaf. So somehow the leaves nearby of the same dimension, which is minimal close by, are all isomorphic as manifolds with S. And also the cohomology varies in all possible directions and, well, also both injective and surjective. So it gives you an isomorphism between these two. And I call this property 3. So now rigid Poisson manifolds I'll define as having these three properties, but first of all I have to explain how to write this in general for any Poisson manifold. And this is what I'll do next. So you start with the general Poisson manifold and consider as omega S a symplectic leaf. So, of course, S omega S, you can think about omega S, well, it is the inverse of the restriction of pi to S. Now you can consider the next order, well, the first order jet. And the first order jet of pi at S, the best way to encode it geometrically is as a transitive Lie algebroid. So this one, and I'll put here quotation marks, is a transitive Lie algebroid, which is simply the cotangent Lie algebroid of M restricted to S. This is a transitive Lie algebroid. And you can make this equality pretty precise in the sense that, well, such first jets of Poisson structures correspond to transitive Lie algebroid structures on this space with an extra property. And for fixed points, well, if S was just a point, this is a Lie algebra and it is isotropy Lie algebra at that point. Now, being a transitive Lie algebroid means that its anchor, which is just pi sharp, is surjective, and its kernel is a bundle of Lie algebras. Right, so this is the kernel. So GS it's actually a Lie algebra bundle, and at every point you can look at its isotropy. And at every point on S, this is called isotropy Lie algebra. Okay, and the next thing what I'd want to do is to define this map. So such a map you can always define in a canonical way. And this works as follows. So first you can consider just the abelianization of this transitive Lie algebra. So the abelianization is simply AS AB. You mod out by the commutator of G and G. And it is very easy to see that this is an ideal inside G. The quotient inherits the structure of a transitive Lie algebroid. And its isotropy will be simply the abelianization of the isotropy. Okay. And in some sense, infinitesimally, this Lie algebroid, in this notation, well, it plays the following role, but well, this is not precise at all. So this is the cotangent Lie algebroid of sigma restricted to S, where sigma are the points where the rank is equal to the dimension of S, right? So this is what it means geometrically, but of course you can't be very precise. This sigma could be, for example, just S. The rank might just jump around S, and here you might still have something. So, okay, so this is just geometric picture. And now having and the special property of this Lie algebroid is that its isotropy is abelian. So, and for such Lie algebroids, you can write them in terms of, well, I'll just say. So you can always decompose a transitive Lie algebroid using a splitting as the tangent bundle of S plus its isotropy. And after you do this, the Lie bracket becomes something like this. Beta. On the first factor, you simply have the bracket of the vector fields because the anchor preserves the brackets. And then, well, you have some more terms. So just write them here. Alpha plus eta of x and y. So of course, you don't have a mixed term between, well, you don't have a term which computes somehow the bracket of alpha and beta because the isotropy is abelian. And these two structures, so nabla, you can see that, well, it is a flat connection on the abelianization, and eta is a two-form on S with values in the abelianization, which is closed for the induced differential, the differential induced by nabla. So d nabla eta equals 0. And now, because the connection is flat, you can trivialize the bundle over the universal cover of the manifold. So let me just write this here. So call S tilde the universal cover. You can just pull it back. And up here, you can trivialize it using parallel transport. And what happens is that then eta, if you pull it back, eta becomes, you can view it as a closed two-form on S tilde with values in, I'll just write tensor GXAB. Okay, so this is now, we're S tilde, so this is the universal cover. So now we're very, very close to this map here, and you simply now view this eta, you take its cohomology class, and you view its cohomology class as a map from the dual of the Abelianization to the second cohomology group, but now of the universal cover of S. And I'll denote this by delta x. Right, so this is basically just the cohomology class of this eta tilde. Okay, and this, let's call this the cohomological variation at x. Okay, I hope this definition is clear to everyone. If you have questions, just ask. So I will call a Poisson manifold M pi rigid at a leaf S if the following three conditions hold. So the first one is very similar that we had for quadrant orbits of semi-simple compact Lie algebras. Well, all of them are. So S is compact, and its first, well, and its fundamental group is trivial. Then second, we assume that the isotropy Lie algebra Gx for x in, so let's take also x in S, Gx is compact. And a third condition is that this cohomological variation map is an isomorphism. It's a linear isomorphism. Okay. So, I mean, I will give later also an equivalent definition of being rigid at a leaf. But somehow geometrically, this is what it means. Well, the leaf is compact. The isotropy Lie algebra transverse to the leaf is compact. And delta x being an isomorphism means somehow that, well, the cohomology varies in all possible directions and exactly once. And that varies in the abelian part of Gx, right? And somehow the semi-simple part, well, you cannot really touch that. And so this is the first definition. And the second I will call M pi S compact at S if, well, 1, 2 hold, and also instead of 3, I'll only assume that delta x is injective. Right, which means that, well, maybe you don't have all the directions. Now, one property that you can see immediately is the following. So, well, now I want to explain this property that a Poisson submanifold of a rigid Poisson manifold is S compact. Okay? So if you take like a leaf which belongs also to a Poisson submanifold of M, then you obtain a surjective Lie algebroid homomorphism from the restriction of the cotangent Lie algebroid of M to S to the restriction to N of the cotangent Lie algebroid of N to S. And this one is surjective. Right? So, and let's also assume that this one is rigid. Okay? And if you look at the isotropy Lie algebras, well, they sit inside, and of course you'll get a surjective map of isotropy Lie algebras, which implies automatically if the first one is compact, any quotient of it will be also compact. So it follows that this one is compact. Okay? And then this one being surjective, it implies it's surjective also on the Abelianizations, and therefore the dual will be injective. So the map from the dual of the Abelianization to the dual of the Abelianization of G, this one is injective. Okay, and then, well, you can look at that construction, and it's actually pretty functorial, and you can see that this map intertwines the two cohomological variation maps, delta x. So if we assume now that this one is an isomorphism, it follows simply that this one is injective. Okay? Right, so what we have proven is, well, if m pi is rigid at S, this implies that n pi n is S compact at S. Okay, so next I want to explain also, to give an equivalent definition, which is much more, well, from a different perspective on these conditions. And this uses what it's called
So is M+1 and S is a leaf? Is
yes.
S a symplectic leaf in M?
Yes, I think I'll always denote by capital S a symplectic leaf. Which one?
The one on the very left, very, very left.
I don't understand the question. So,
No, there's a theorem you wrote very, very beginning.
yes.
Is that also S is a leaf?
No, this is small s. Yeah, it's S compact.
This is something else.
This is a property.
And this one was,
And this is a leaf. And this is S compact. So this is the definition. Maybe I'll write it like this.
so but here, does, is there a, are you fixing a leaf in that?
No, no.
You're not.
No, so here, S compact, I mean S compact at every leaf, and rigid, I mean rigid at every leaf.
So you're telling us something about individual leaves, but eventually you're going to tell us something about a whole.
Exactly. Mm-hmm.
So
Mm-hmm.
is the end of your theorem,
So here, I think, I mean, here I only wanted to explain this thing.
So then in your definition of rigid, when you write S compact, you don't mean the property S compact, you mean S is compact, right?
No, M pi
No, up there.
is
Number
S
one,
compact.
capital S is
Yeah,
right, right. So it's not the property S compact.
no,
Statement.
no, yes. So rigid means the leaf is compact as a manifold, the fundamental group is trivial, and the Lie algebra is compact, and this map is a linear isomorphism, and then as compact, you just drop this last condition, you assume it's injective. And here I wanted to explain that the submanifold of a rigid one is automatically S compact, and of course, it also follows that the submanifold of an S compact is also.
So here you have this notion for an individual leaf.
Yes.
I guess you're sort of working your way towards defining what it means to be
Right, so
compact in general.
Maybe it's good to keep in mind that in mathematics, the red herring doesn't be neither red nor herring. So this compact doesn't assume there is no S. It's just an A. S compact.
No, but
There is no S.
in these definitions, what is everywhere? I just want to understand correctly that this is sort of an intermediate definition.
yes, it is an intermediate definition. So, okay. So I can just say it now. Rigid, I mean rigid at every leaf. S compact, I mean S compact at every leaf, if I don't specify.
And then individually, you just told us what it is,
Yeah?
and then I should just add the
What?
modifier for all.
Yes, yes. Okay. But I want to give now an equivalent definition of this, well, an equivalent way to say this thing. So to every Poisson manifold, you can associate a Lie algebroid, T star M. And then to the Lie algebroid, you can associate an object which is called the Weinstein groupoid of the Lie algebroid. So this is the Weinstein groupoid. So this is, it's only a topological groupoid, so it's not a Lie groupoid. And it was constructed by Conn and Fernandez in their paper on integrability. And it's an object canonically associated to this Lie algebroid. And in terms of this object, you can rewrite these properties very easy. So first of all, S compact at some point x in S. This one is equivalent to the S fiber of that point B compact. And actually, this is the way I usually think about this property, S compact. Now, I mean, but that's somehow the geometric interpretation of this property. And then rigid at x. So rigid at the point in the leaf or rigid at the entire leaf, they are equivalent. This is equivalent to the following three conditions. So first of all, S at minus 1 of x is compact. Then S at minus 1 of x is, well, let me just write Hausdorff. In fact, this property of being Hausdorff, it is equivalent to it being smooth. So it has a natural smooth structure in case it's Hausdorff. And then the third one is that its second cohomology group vanishes. Second deram cohomology group vanishes. Okay? I'm not going to prove this, but, well, this is a different way to think about them, if you know what these objects are. Okay, so my plan is somehow also to explain a bit what goes into the proof of this theorem. And the proof is based on two results which I have in my PhD thesis. And that's the next thing I want to state, these two results. So the first one is a normal form theorem for rigid Poisson manifolds, so rigid at a leaf. So this is theorem, I'll call it theorem 1. Which I did with my advisor. And it says the following. Well, if m pi is rigid at S, it follows that pi is linearizable around S. So in the case of fixed points, rigid at a leaf, well, it means that this S fiber is compact Hausdorff, and so on. But this S fiber, in fact, is just the one connected Lie group integrating the isotropy Lie algebra. So for that one to be compact, that is equivalent to the Lie algebra be semi-simple of compact type. So in that case, you obtain back Conn's theorem. And, well, I mean, it's not very easy to explain what this linearizable at S or around S means. You can write down a normal form for the Poisson structure around S. But what I want you to keep in mind is the fact that we understand, let me write this, so we understand pi around S. right? So one of the consequences of this is, well, as a corollary, you obtain that rigid at S implies also rigid around S. Okay, so if it's rigid at one leaf, you have the normal form for the Poisson structure, and you can just check that around that leaf, what you obtain is also rigid. So at every leaf in a neighborhood. Okay. And then next, the second theorem that I will use for that is also from my thesis, which I like to call the rigidity theorem. So which basically tells you that rigid Poisson manifolds are rigid or have no deformations. Okay, so we start with the Poisson structure, which is rigid. And here by rigid, of course, I mean at every leaf. Right, then the following holds. Well, I mean, it's a bit hard to state. I think whenever I gave a talk, I stated differently. Let me try to be now a bit more concise. So it doesn't have deformations for an invariant open neighborhood or an open sets, but it's easier to state it around the compact Poisson submanifold. So if n inside M is a compact Poisson submanifold, then there is an open neighborhood of n, let's call it V, containing n V bar, and I'll assume that the closure is compact. And these actually, I mean, these are like some small tubular neighborhoods, so they can be taken arbitrarily small of the Poisson manifold, such that pi is rigid, but sort of around n. So that if you take a second Poisson structure on M, which is Cp close to pi. I mean, Cp in the Cp topology, where P is, in fact, a number which depends only on the dimension of your manifold. So which is Cp close to pi. Then it follows that they're basically isomorphic and on V. So it follows that there exists a Poisson diffeomorphism phi from an open neighborhood, well, on V defined, and pi tilde restricted to V to its image. So phi of V and pi tilde, pi restricted to phi of V. And also phi is C1 close to the identity. So with phi C1 close to the identity. Okay, so it simply tells you that you cannot deform the Poisson structure. If you take a very, very small deformation, and you can even fix beforehand an open, and on that open, if, well, the deformation was small enough, they are isomorphic. So the restriction of pi tilde to this open is isomorphic to this open set is isomorphic to the restriction of phi to some other open, which is also C1 close to the original one. Okay. And this result is pretty powerful. So in particular, let me call it theorem 2, it also implies the linearization result.
What is V? Is that just the definition of V inside M?
Yes. It's a small diffeomorphism from.
Is V going under your assumptions? Is V going to be unique?
Well, up to, I mean, you can always precompose it with something, but yeah, I don't know what you. Not really. No. No. Okay, so, okay, now my plan is to basically prove the theorem using these two results in, I mean, not globally, but at least locally around the leaf, just for you to get an idea how the proof goes, because using these two theorems, the proof is actually very simple locally of this theorem. And let me just call it like the main lemma. Which says the following. So if you start with a Poisson structure that is S compact at a leaf, at S, then it follows that a neighborhood of S can be embedded into a rigid Poisson manifold. So, and the proof is pretty easy. So, first what you, okay, and to simplify it even more, I'll assume that the fundamental group of S is trivial. In general, you can just do basically the entire proof on the universal cover of S and then do it. Pi1 invariant, Pi1 is finite. This is one of the conditions of being S compact, so everything works. And then you do the following. So you take some neighborhood U of S. Let's say S is in some U. And on this U, you construct some two forms, which I'll specify a bit later what properties they have. Right? So let's say from I is from 1 to some n. And then let's also denote. So for T in Rn, I'll simply denote by sigma t the sum of ti sigma I. Okay. And then the final Poisson structure that you'll construct, so which is this m bar pi bar, is on u times Rn. And now you'll see exactly the construction that we did at the beginning, but we have to write a Poisson version of this construction. So I'll write with pi sigma, where this pi sigma is a Poisson structure that is tangent to this submanifolds, u times t. And on such a submanifold, it is simply the gauge transform of pi by sigma t. So this gauge transform is an operation which, well, it's usually well defined in the Dirac setting. So you obtain a new Dirac structure, but because at t equals 0, these forms are 0, it will actually be defined on a neighborhood of u inside this product. Okay, so around u, pi sigma is well defined. And then you can also see that the Lie algebroid of this new Poisson manifold restricted to S. S as space is just AS times Rn. So in particular, its isotropy Lie algebra will be just a product. So isotropy is just Gx plus Rn, hence also compact. And what is more important, what we want to do is to make this cohomological variation, this map delta x, be also surjective, right? So this is what I want to write next. So the map delta x works as follows. Maybe I'll write this here. delta x of this bigger Poisson manifold goes from gx ab star plus Rn to H2 of S. And this is simply the pair, well, it's basically delta, so it sends alpha comma t to delta of alpha plus, and now it's the sum of ti times the cohomology classes of sigma I restricted to S. Okay, so you just need that this map is a bijection, is a linear isomorphism. So for this, well, you need that this restriction, sigma 1 restricted to S and so on, sigma n restricted to S, be a basis for a complement of the image of delta x. Right, and then you make this cohomological variation an isomorphism. And then if you choose these sigmas in this way, of course, you can extend them to some open U around S as closed forms. And then it follows that the Poisson structure that you constructed, pi sigma, this one is rigid at S. Okay? And as I said before, rigid at S implies also rigid around S. And of course, now U pi sits inside here as a Poisson submanifold in U times Rn by sigma, just embedding it with 0 on the second component. Okay, is this clear, this argument? So you just complete it like this. Well, I have 2 more minutes, or I don't know exactly. Yes? Right, so, and then, well, there is the issue of actually making this argument global to embed it properly, the entire manifold. Now, about deformations, how this works, and I'll just tell you, I'll just catch a bit the argument because that's also pretty simple. Well, just look at this construction, right? So you start with pi, and then you construct this pi sigma. Now, if you start with some pi tilde, which is Cp close to pi, it follows that pi tilde sigma is Cp close to pi sigma. Right? But this Poisson structure is rigid around us. So it will be isomorphic. Yes. So this Poisson structure is rigid, so any deformation of it will be isomorphic to itself around S. So you obtain an isomorphism from some open V inside U times Rn pi tilde sigma, a map phi to phi of V and pi sigma. So this is basically by theorem 2. You obtain this isomorphism between these two Poisson manifolds, but now this one, of course, has as a submanifold V intersected with U with pi tilde. So this restriction, phi restricted to V intersected with U, well, this is exactly this map I tilde from here. So this one will map onto a Poisson submanifold, of course, phi of V intersected with U. And pi tilde restricted to this phi of U intersected V. Right, so, and this is the trick how you can study deformations. So whenever you deform this a little bit, you obtain it as a submanifold inside the rigid Poisson manifold. Okay, is this clear? This argument, I'm done. Thank you. Yes. It doesn't have to be smooth, but it has compact as fibers. All the source fibers are compact. So the Weinstein groupoid of the cotangent Lie algebra has compact as fibers. And also, as a consequence just of this main lemma, it follows that if it has one compact S fiber over one point, then the nearby S fibers are also compact, because it can be embedded into a rigid one, and that one has all the source fibers. So being S compact is also an open condition on the manifold, but also via this deformation argument, also it is CP open.
Then you motivate this theorem by saying that this helps you to compute the modular space of the given S compact for some reason.
I mean, also in this case, if you just write this restriction, you know already how it is deformed, right? The example that I have is this of the sphere inside the dual of the semi-simple compact Lie algebra, and therefore, and in that case, nearby spheres, which are Poisson manifolds, you can parameterize them by invariant functions on the sphere. This gives you also a global definition of this deformation space. But you can also do it, well, in this abstract setting. I think this should work to actually give a description of the moduli space of Poisson structure near such an S-compact Poisson structure.
How is S compactness related to S being
To S being a proper member.
I mean, that property is considerably stronger.
So the thing is that, well, the groupoid itself is not even, like, it doesn't have Hausdorff S fibers. But I don't really know. I mean, this theorem implies that, I think it implies, yeah, no, the theorem should, I think, should imply that if it is S compact, then the map is proper, yeah, in the sense that we know.
Do you have an example of a rigid one which is not integral?
A rigid one which is not integrable. No, a rigid one is automatically
It has to be integral, right?
Yes. Yes.
Then it has to be S code.
Yes. And there is also this class of what you study of S, how do you call them? Of compact type also many, where the Weinstein groupoid is also smooth. Basically, it's smooth and S compact. That's what it means. And here we just drop this condition of smoothness, and somehow in the leaf space you lose this affect structure.
But what, I mean, smoothness is only for the cement, for the S compact. The rigid ones are smooth.
The rigid ones are smooth.
Yeah, the point is that it's like the sphere of the blue of the wheel, which is not.
And being integrable for these S compact structures, I mean, that's a very unstable condition. If you deform them, won't be.
Any other questions?